So thank you for your kind words, and let me add some words in return, that we thank you and the ICTS for the hospitality here. Remco and I are members of the management team of the Big Networks program. The Networks program is a 10-year program about networks in the Netherlands, funded by our Ministry of Education. Many people are involved, and we have been very pleased to have extensive interaction with India. It was not only ICTS, but Mumbai, Delhi, Kolkata, and Bangalore were involved. And we've seen in the last couple of years many Indian people, both senior and junior, coming to the Netherlands, and also people from the Netherlands coming to India. And it's been an enormous joy working together, because we share a lot of things in common, and one is the enthusiasm and the fun that we have in doing that. So let me express our gratitude on behalf of the Networks program for all these activities. And on a personal note, I was extremely pleased when you invited me to become a senior faculty associate member. I immediately said yes. So in the coming years, I'll be coming here regularly, and we'll be able to see first-hand experience how this beautiful institute is continuing to develop. So thank you so much for that.
Thank you for your Thank you for the very kind words, and we look forward to more network meetings at ICTS, and to Frank and others visits from the Netherlands as well.
Yeah, thank you.
So our first speaker, we should do a little bit but organically as we go along. So our first speaker is Frank. He needs no introduction. So the friendship paradox for sparse random graphs.
Yes, the friendship paradox is a paradoxical fact, but it's a true fact. And let me tell you what it is. And many of you will have heard of it, and maybe others will not. A social scientist about 30 years ago came up with the phrase, on average, our friends have more friends than we do. Now, the first time you hear this, you say, well, that's not possible. Come on, it sounds like we are all below our average. I mean, that's not possible. Still, it is a fact. And the fact is actually having a simple reason. If you are a part of a social network, there will be some people who have very many friends. You are more likely to be a friend of these people because they have so many friends. And therefore, you will be more likely to be connected to people who have many friends. And that's a bias that causes the fact that if you look at the friends of your friends, they are more plenty than the friends of you yourself. So it sounds paradoxical, but it is a fact, and it's a hard fact that. Yeah, you can. Right, if you want to turn it into a positive, our friends have more enemies. Yeah, so there's a bright side and a gloomy side to look at this. Yeah. Yeah, and you can talk about other sort of properties that you could do. Okay, I'm going to formalize it a bit because we have to see what this is going on. So you think of a finite undirected random graph for the moment, and it has n vertices, and they are labeled by 1 up to n, and di will be the degree of the ith vertex. Okay, we've seen this many times. And then the quantity to look at is what we call the friendship bias of vertex I. And how do you define it? You define it as the difference between two numbers. One is the average degree of the neighbors that you have, because the degree expresses the number of friends that your neighbors have, and your own degree. So it's the average over all your neighbors of the number of the degree of all your of your neighbors minus yourself, And when you are not connected to anybody, you don't know what to do, and you give this number, you call it 0. And Aij is just the ijth element of the adjacency matrix, and it just counts the number of edges between I and j. So it's possible to have multigraphs. We are not necessarily excluding that. Okay, so this is the bias of vertex I, and you now make up the empirical distribution of these numbers. So every vertex has its friendship bias, and you make up the empirical distribution, and this becomes a probability distribution, a random probability distribution if your graph would be random, and you can average over the graph if you want to. So this is a key quantity that describes what all the friendship biases in your graph are. And the friendship paradox, now written in mathematical language, is for any graph that does not have self-loops, but it may have multiple edges, the average friendship bias is non-negative. So if you take all these biases, friendship biases for all the vertices, and you average them over all the vertices, and give that a name, then in terms of this empirical distribution, that's just the mean of this empirical distribution, this number is always non-negative, no matter what graph you pick, as long as it doesn't have self-loops. And you can also show that this is 0 if and only if your graph is such that all its connected components are regular. It means that every connected component, all the vertices in that connected component have the same degree. And if the graph would be connected itself, it would mean the degree is the same. Everybody has the same number of neighbors. And then, of course, there is no bias because everybody is the same. But as soon as the network is not homogeneous, this is strictly positive. And that's a fact that you could prove. And let me go through a computation very quickly. Do not bother about the details. So this average friendship bias, here we fill in what this friendship bias was as the way we have defined it. And then, because this matrix is symmetric, you can sort of do a symmetrization trick and write this as a sum of squares. And because the adjacency matrix is symmetric, because you are an undirected graph, and this is a manifestly non-negative quantity, and the only way in which this becomes 0 if all these squares become 0, and that means that you are constant degrees in, let's say if your graph is connected, you would be a constant degree. And so yes, there is this friendship paradox, and it's actually not a paradox, it's a fact. Okay, so what are we going to do? We can ask the question, well, fine, there is there's this friendship bias, but is it big or is it small? How many vertices have a positive bias? How many vertices have a negative bias? What happens if the graph is random? So in general, the question, how do you quantify the friendship paradox? What can we say about this? And that's what we did in the paper that appeared shortly before Christmas by Rajat, Hazra, and Azadeh, who is a postdoc in Leiden, and myself, and we put it on the archive, and it contains several aspects of trying to quantify the friendship paradox and also seeing what this quantification really becomes when we take standard, let's say classical random graph models and see what happens. And so the remainder of the talk will be all about this. Can we quantify this friendship phenomenon? Okay, and I'm first going to talk about convergence. We will be interested, as always, in taking very large graphs. As Pim already said in the first talk, things become very nice when you take limits. And so we're going to do that too. And so before I can talk about specific examples, I have to do a little bit of discussion about what convergence are we going to use. Since we're living, I decided to talk about this for sparse random graphs. There is a notion of local convergence that we need in order to quantify this object. So local convergence is basically saying, in very simple words, if I have a random graph that becomes very large, and I randomly pick a vertex and I look at what the graph looks like around this randomly chosen vertex, does what I see converge to something random? And if that's the case, you speak about local convergence. So Remco in his books also talks about that, and it's a very powerful tool. It was already mentioned before. Pim also mentioned the notion. So I will have to very quickly mention that because we need that tool in order to be able to go on with the friendship paradox. So we're going to have our graph. We're going to randomly draw a vertex and then start to look at what you see around that randomly drawn vertex, and if that converges to something, and what it should converge to is a random graph G infinity with a root, then you say that there is local convergence of your sequence of random graphs. And you need to be careful about how you do that. You work in the space of locally finite rooted graphs. You need to define a certain topology. I will not go into those fine details again. And basically what you're doing is you have a sequence of finite random graphs, and you pick a random vertex and you say, what is the connected component in that graph in which my uniformly chosen vertex finds itself? And you see that whole thing as a rooted graph with root vertex as a vertex, and you want to pass to a limit, and you hope and expect that you're going to see a limit if there's local convergence. And there are two ways in which local convergence can happen. You could say, I'm going to average over the graph, and I'm going to average over the randomly chosen vertex. This is just a choice from the set 1 up to n. And if I have a bounded and continuous function h, and that converges to a limiting expectation, then you say that you converge locally weakly, and that your limit is indeed a random rooted graph with root phi. And these will have laws prior to you taking the limit n and after you've taken the limit n. So these are notations. And there's also a convergence where you say the average is only taken over the randomly chosen vertex, but you condition on the graph. And if that is still converging, then you talk about local convergence in probability. So these are two notions. Both are important, and they are doing nothing other than saying, pick a large graph, pick a random vertex, look at what you see around the vertex. Does that converge to some sort of rooted random graph? And for many sparse random graphs, this convergence is indeed occurring. And that is something that we will need to quantify the friendship paradox. Okay, I'm going to define how we're going to look at this random rooted tree that is supposed to be occurring as a limit. And this will be, because it will be a random tree in the limit, because we're dealing with sparse random graphs, and sparse random graphs are locally tree-like. So in sparse random graphs, we expect to see rooted random trees appearing as limits. So in such rooted trees, I will call phi the root, I will call d phi the degree of that root, and I will call dj the size of the offspring, so the further degree downwards of the jth neighbor of phi, and there will be a number that I define in terms of all these degrees, and that number sort of reflects, it's sort of the the limiting analog of what this this friendship bias would be, you take off the degree of the root, but you take the average of the degree of all the neighbors of the roots, and there's a +1 here because each neighbor does not. Each neighbor j not only has dj neighbors down, but it also has its up connection with the root itself. And so this quantity should be the limiting random variable that describes the limit, if you converge to a random rooted tree, of your friendship bias. And this has a law, which we call mu. And if Gn converges locally in probability to such an object, then the empirical distribution of the friendship biases will converge to the law of this random variable. So that is the first theorem that we prove. Not very difficult. It's an immediate consequence of local convergence. And if it converges locally weakly, then in fact, the expected value of the friendship paradox empirical distribution will converge to mu. So what these theorems are telling us is that if you have a random graph whose local limit is a random rooted tree, and we know for many graphs what that random rooted tree would be, then all you need to do is to study this quantity associated with that rooted random tree and study its law, and this will give you a description of the limiting behavior of your friendship bias. So the question could be, so we know that this on average has to be non-negative, but is it typically large? Is it typically small? This can take positive and negative values. Is it such that the mean would be very big, but still 99% has a small negative value, and there's a very small percentage of having a very big value? What is the law of this object? So that's what we're going to talk about. Okay, so the local convergence, which we know applies for many large random graphs, has been put to use to say, if you know what that local limit is, there is an object here, very explicit, that you need to study the law of, and that law is going to tell you, it's going to give you the quantitative aspects of your friendship paradox. Now, we're going to look at various aspects, and there's one particular aspect that we try to look at, and that was saying, we introduced a notion saying, is a friendship paradox significant or insignificant? We know that this measure mu always has a non-negative mean. That's always true. So the integral of x, mu dx, is non-negative. However, it could be that you say, it could be that more than half of the vertices have a negative bias. And you say, okay, their average is always positive, but it could be, as I just said, 99% of the weight is on negative bias, and there's one guy out there who sort of completely biases. And then if that would happen, you would say, well, we would say that would be a sort of insignificant friendship bias, because the friendship bias is there, but not really in the full sense as you would expect it. And if you say more than half have a positive bias, then we call this, then the friendship bias would be significant. Perhaps this number would be very close to 1. It could be that almost everybody has a positive bias, and then we would call it, extremely significant. So this is an interesting notion that we are going to look at. Nelly.
Okay, so but on the previous slide, it does need to be locally tree-like, right?
Not all sparse graphs have a local limit.
No, not all sparse. I'm presuming that I'm having a local limit, because otherwise I cannot continue in quantity.
But for this theorem 1 and 2, is it important that the limit?
Sorry, it's important that?
That
Yes, for what we want. For this formula, it's important that it's a tree because I'm only looking at the root and the neighbors. And in sparse graphs, this is typically what is happening. Well, I'm assuming that it's going to happen. Sure, I'm assuming that it's going to happen. And
But I think what Nelly asked is whether theorem 1 and 2, the convergence to something involving a local limit is true more generally.
it is true. It's true more generally.
So is it a local property?
Yeah. No.
It is a local property.
Yeah. And it's a more general property, and it does not require a rooted random tree. So thank you for that. And since all cases that we're going to talk about will be trees, then we have a nice explicit formula for it. But it is more general. Right. Good point. Okay, sorry. Same question. Okay, very good. That clarifies a lot. Thank you. Okay, so and it turned out that this notion of significant versus insignificant raised a number of problems, and I will tell you about that. In particular, it led us to believe in a certain very classical inequality that we cannot prove. We've been talking with Rob van den Berg, who's a specialist in probabilistic inequalities. He also doesn't recognize it. And so something funny came out of this story. So I'm going to talk about 4 examples, but in view of time, I think I'm going to only be able to talk about 2, where you take a random graph that would fit into this picture that has a local limit that would be a tree, and then start to see what we can say about this limiting measure and is there significance or insignificance? What else can we say about this distribution of the bias? And all of these models are very classical, and Remco's book, 2 books are great places to learn about them and to see all sorts of very delicate properties that these models have. And I'm going to start, of course, with the classical Erdős-Rényi random graph, and it is a homogeneous version where you say, you pick a parameter lambda, you've all seen this, you pick a number of vertices, and the graph that you look at is the Erdős-Rényi random graph in which every pair of distinct vertices gets an edge with a probability that's lambda over n, and you have to majorize it by 1 because it has to be a probability. And we're going to let n go to infinity, and lambda is going to be fixed. And it is well known that if you take this graph and you let n go to infinity, that this will converge locally in probability to a standard Galton-Watson tree, whose offspring distribution is the Poisson distribution with that parameter lambda. And using the formula that I wrote down before, which only applies to trees, but we have here a Galton-Watson tree appearing as the limit, the total weight of all the vertices that have a positive bias, you can write out as a sum of Poisson-like terms. And you look at this thing and you say, that's all explicit. Let's derive 20 properties from it. And you chew, because this is not such an easy formula to deal with, because there's a k to the power L here. And in fact, we proved that if you take lambda to 0, then this model will be fully significant. So there will be no vertices who have a negative bias, but lambda going to 0 means a very sparse setting. And it's a setting where all the vertices are almost isolated. And so that's not really a very interesting thing, but nonetheless, this is a fact. And if you make lambda go to infinity, you drive it to the borderline of being significant. So for very large lambda, when the graph gets very dense, you will see that approximately half of the vertices have a positive bias and half have a negative bias, so you're still significant.
So in B, if I were to make it the open interval,
Yeah.
you get 0?
No, we believe that the 0 doesn't. Oh, in this one, yeah, then you would get 0.
That's because
Yeah,
you basically
yeah, because there's
only
no,
of
yeah,
edges,
yeah.
and then the degrees on both
Yeah.
sides of the edges are the same.
But the value 0, you need to give it some special attention. But I think I don't want to.
Well, there's a
Yeah.
difference between the degree being 0
Yeah,
and
yeah.
your
Absolutely.
bias being
Yeah,
0.
right.
Is this monotone in lambda?
Here's an interesting picture. So we were asking, can't we prove that it's positive for all lambda and that it would be going monotone down? We have been unsuccessful. Even this simple expression is not nice. And in fact, there is a certain classical inequality that you would need to do that. And we've been looking at this and we failed to prove this. And even, talking to Rob van den Berg, they said, well, he says, I don't recognize this as anything I've ever seen before. I said, well, so there's a challenge here to do that. But if you plot this numerically, you will see that the fraction of of positive biases goes down, and there's no mystery because this formula here is, you can put it on a computer. I mean, it's nothing magic about it, but analytically, it's not so nice. And we have been able to prove what the mean and the variance of your bias distribution mu behaves like. And we've also computed a tail of, so what is the probability that you have a very large bias, and this sort of drops off like slightly faster than exponential with a certain power law correction. So we are able to say in detail what the tail of the distribution that you have a very large friendship bias is like.
It looks very much like the tail of some.
Yeah, it is related. Yeah, it comes from the tail, but you need the Poisson's distribution. You still need to sum over all sorts of things because the formula I wrote down. But of course, it comes from Poisson. Okay, in view of time, we were also looking at an inhomogeneous version of the Erdős-Rényi random graph where you would have a sort of control function, and then depending on how big I is divided by n, you would have different probabilities. And I'm going to skip that because there is not enough time. Okay. The third model we looked at, and for the inhomogeneous Erdős-Rényi random graph, many things were similar. There were some differences. The moment you bring in inhomogeneity, it has an effect on the distribution of your friendship paradox, and certain things really change. And again, we found more complicated expressions for this probability distribution mu, but again, numerically, it appears that everything is always significant. Again, we don't understand really why that is happening, but that does happen, and it depends on certain probabilistic inequalities that we have not really understood very well. A very classical model that we also looked at here is the configuration model. So the configuration model, you have seen this many times before. You pre-assign to every vertex a degree, and you get a whole degree sequence, which we indicate by a vector dn. And the configuration model is just a model where you say, I look at the set of all graphs that have this degree distribution, and then I uniformly at random draw from this class. And there's a classical algorithm how you do that by matching pairs of half edges. And there are issues like, is your graph going to be simple, yes or no? Could I, if there are self loops, can I trim them? So these are all subtleties that I'm going to wipe under the rug, but because we can incorporate those or not incorporate those, and it doesn't really change so much the story. And you need to make sure that this degree distribution is decent. It has to, if you randomly pick a vertex and look at its degree, then you want that this random degree has a limiting distribution, and this limiting distribution should be reached in L1 norm as well, and the limit should be assigning positive value to, it should only allow positive values of the degree, so there are some conditions. And then it is known that if you look at the local limit of such a configuration model, you will end up again with a random tree. And the random tree is such, a rooted random tree, such that the root has an offspring distribution that is just given by this limiting law D. And all the offspring, the offspring of the root have a bias distribution, which is indicated here by P star, and it's just that you take the distribution of the root and you bias it. So there are in this case two offspring distributions that describe this limiting random tree. All very explicit, and if you choose a nice degree sequence such that this convergence is happening, then you have found what your local limit is.
This looks a lot like inspection paradox.
The
Inspection paradox and renewal theory.
yeah, this is again a bias. This biasing is also a fact. So if you do the exploration algorithm, you will see this is coming up. Yeah. So this bias is happening in many different contexts. Yeah.
Can one make a connection, maybe?
I haven't thought about that. No.
So it looks a lot like the waiting time paradox.
No, inspection. If you randomly inspect when people like they're arriving, they're likely to pick a interval which is larger.
Yeah, it's exactly the same one. Yeah.
Okay, so what did we find for the configuration model? There are many things you could do, but we say let's focus on one particular offspring distribution, which is an algebra has a power law tail with parameter tau, and we call this the Riemann offspring distribution. And this tau is a parameter that sort of modulates the presence of the hubs in your limit. And
The zeta distribution.
okay, the zeta distribution. Well,
That's the zeta function, right?
that's the zeta function, the zeta distribution. Okay, so let's focus on this class, this one parameter class of offspring distributions, and see what the friendship paradox is going to do in that particular case. Of course, you can go beyond that case, but let's focus on this case and see what we could do. And here, we found that there's always significance in this model. We can prove now that no matter what tau you pick, you will always be significant. More than half of your vertices are going to have a positive friendship bias. And both when you let tau go to 2, so very thick tails, and tau going to infinity, very thin tails, you converge to full significance. And so that's different from what we saw for the Erdős-Rényi random graph. You are at both ends, you're going to become fully significant. Almost everybody has a positive bias in this model, and that is no doubt also related to the tail properties.
What happens if you exclude 0?
I don't know offhand. I think it would not be a problem. I don't think it would be a problem. I think this would probably be true also with 0, but I have to look at that.
This is not monotone in tau.
This is not monotone in tau, no. And I'll show you a picture in a second. We also were able to compute the first and the second moment of your bias a random variable, and they come in moments of your limiting degree distribution. So this is a bit more Baroque, but you can prove certain inequalities that the variance of your bias function is always at least as big as the variance of your degree, for instance. That follows from these facts. And the tail of your bias also shows up with the same exponent tau. There are some constants in front of here that are complicated, but it says the tail, the tau will also reflect itself in the tail. And look, here's a picture of sort of analytic bounds that we were able to say as a function of tau and the total weight of the right half line, and it is sort of sitting in this region. It's always above 1/2. It's in fact rather large. It's always above 0.87 analytically, and at both ends, it seems to say that you are becoming fully significant. So no monotonicity in tau, very different from what we saw for the Erdős-Rényi random graph, and that's it. Siva, how much time? Yeah, yeah, please.
The diff, right? So you have upper and lower bounds, right?
Yeah.
We conjecture that the diff is around tau 3, basically the point where you switch from finite to infinite variance, or?
Good suggestion. I have no answer to this. I think we do not, our formulas are not exclusive. It's certainly not that from our formulas we would see that everything becomes minimal at tau is equal to 3. But it's apparently, I mean, tau 3 is an interesting thing, of course, with the second moment.
When you have finite variance.
Yeah.
Thing. So in the previous bound, you could show that if you are at tau between 2 and 3, the variance of the delta phi is infinite.
Yeah.
From there.
Yeah.
So, and all about, so you get bounds, you have expressions, but like they're not very explicit enough.
Yeah. Okay.
No, analytically, they're a bit complicated. Yes.
But maybe it's because there are two different reasons for this bias. So at tau between 2 and 3, maybe because everybody has a huge neighbor, while after bias is finite, it's just for a different reason.
That may very well be. If I look at the formulas, we are not proving this by chopping it up into regimes. The proof comes all at once, but it might be that if you want to be more precise, that there's some kind of more delicate fine structure that would depend on this tau. That may be the case. Okay, this is my last example. I only have a few slides. What about the preferential attachment model? And I'm taking an example. In fact, I'm only going to take the case where when you bring in a vertex, it only comes with one vertex, with one edge attached to it in order to sort of simplify the formulas. And the preferential attachment model is a dynamically growing graph where you start with a single vertex that has an edge and that has to connect to itself, so it has a self loop. And then you keep on adding vertices, and every time you add a vertices, you do the following. You say, the vertices that are already there, what are their degrees? And you decide to connect to one of those vertices with a probability that is proportional to that degree, modulo a shift, and the parameter delta is doing the shift. And you can also connect to yourself, and you keep on growing your graph like that. So that is the recipe. This is an example of a preferential attachment-like model, and so in Remco's books, this also gets a lot of attention. And the connection probabilities are sort of proportional to the degrees that you see, but there's a shift parameter involved that is very important because it plays a major role in talking about tail exponents. And yes, like in the configuration model, this model will contain self loops, which we didn't want, but you can sort of get a perturbation of this without self loops, for which what we're doing is also going to work. And we know that this has a local limit. This local limit is a bit more complicated. It goes under the name of multi-type discrete time branching process, and it's called the Polya point tree, but we understand this object in detail very well. And so with that knowledge, we could say, let's again look at what our measure mu and this random variable delta phi looks like. Also here we find that you're always significant for this whole class of models, no matter what delta you pick. As you let delta go to its boundary value, it becomes fully significant. The mean of your friendship bias can be, which we know is non-negative, can be quantified, and depending on whether delta is positive or negative, this could be finite or infinite, and we do not have a fully sharp computation when it's finite. And also the variance sort of changes when delta crosses the value of 1. So we have good control over the first and the second moment of our random variable. We do know that this has to be non-negative, and here the quantification makes that much more explicit. And if we want to look at the large tail, then we have, again, some power law estimates. This model is complicated enough so that we do not have matching upper and lower bounds, but at least we have lower and upper bounds that are polynomial, and they come in a tail exponent. The tail exponent of the degree in the preferential attachment model is 3 plus delta. Delta has to be a number larger than or equal to -1, so we're talking about tau starting from 2, and we have some bounds that we couldn't really narrow up to a full asymptotic, so there is a gap between these things, but nonetheless, it again shows that if you want to know what the probability is that you have a very, very, very large bias, they are controlled by tails that reflect this tau in a way that actually depends on whether delta is positive or delta is negative. So that's and the delta was a shift, so whether delta is positive or negative really changes the model. So and also numerically, you see that we have the same phenomenon as we had for the configuration model. You're almost fully significant, and in fact, it's even more dramatic here. Depending on what delta you pick, you will be extremely close to full significant. This is 0.9980. So you are really very close to full significance here. Fine, that's what we find numerically. And so again, also for this model, a fairly complete quantification of this friendship paradox. Here's my last slide to finish up the story. So we have developed local convergence to say, well, we can write something down for our friendship paradox. In particular, it becomes computationally very explicit when your limit is a rooted random tree, which are the cases that we had here, but there is more in life than that, as Remco already pointed out. And then we were able to quantify these things. Some mysteries appeared, some inequalities that we said, well, they appear to be true numerically, can we prove them? And we have been unsuccessful to do that because they involve certain tricky inequalities that do not seem to be of a type that we've seen before. So there certainly is a challenge to make that much clearer. So there is here a question around can we actually do that? And then there were some things popping up where we said, well, that is reasonable, or maybe not. So why are we almost fully significant in the configuration model and the preferential attention model? I have no idea. So there's still a lot of intuition missing, saying, yeah, that's sort of logical because we don't have all the becauses. And the next thing that we're going to do is to look at the multi-level friendship paradox. So you could say, what is the difference between the average number of friends of friends of friends and friends of friends? So I'm looking a level deeper. You can do that. We're going to try and working on that. Many questions open, very challenging, and who knows what we will see. Thank you so much for your attention.
So the level of threshold of significance you chose is 1/2.
Yeah.
Would the story be any different if you had a different threshold?
Would it be different if you?
If you changed half to 2/3, for example?
You could do that and ask that question too. The 1/2 was given by the idea that you say, okay, I know that on average I'm always positive, but it would be strange if you say the bias is on average positive, but 99% of the people have a negative bias, very little, and there's one guy who has a huge bias and therefore their average bias is still positive. So we would call such a situation, the paradox is still true, but we would call it sort of insignificant because really most of the people are not having a positive bias. If you want to put the threshold at 2/3, fine, we can do that computation, but sort of 1/2 is a natural thing to do. And you also see that this 1/2 is popping up in certain limits. So it seems to be the right choice to do.
No, I just have one comment, and because so there was a question about whether this is true for general local, which so we have an expression in the paper for if you have just a local limit G infinity, then you could write down an expression for it. It's in the paper also, like, but it's with these examples, it doesn't make sense because it's much easier to deal with the simplified expression when you have a tree, like it's much more nicer than, but in general, the function is just a local function.
Yeah.
And maybe a question for Frank is, what do you think, what will happen in the dense case?
Well, an easy way out would be grafons, but we haven't thought about that. That would be easy, of course. Then you're going to talk about huge degrees and the degree bias. What will it be? It might be that something interesting is happening after you scale. So I think you would need to do some scaling. Interesting thing to think about. And then maybe after an appropriate scaling, there's something that we could do in terms of grafons. Would be very nice. But it's a different world. Yeah.
Maybe you can, question for Facebook can be, how many people should I block? So this bias becomes arbitrarily close to 0.
Share a block?
How many people should I block? No more friends for them. I take them out. So
yeah, so isolated vertices you can remove.
So that the bias now comes down to epsilon.
Okay. I have no idea.
You're going to take out the people who have the most friends.
Okay, so that would be kind of highly trimmed bias. You're going to look at the people who are in trouble. Okay, okay, good.
So I have a suggestion. Frank.
Yeah.
In your formulas, you always look at the mu of 0 infinity, 0 included.
Yeah.
Zeros plays a special role because they're, and actually in limits it may arise rather frequently.
Yeah.
I would actually attribute 0 1/2 to your decision whether you're significant or not.
Yeah,
because then it becomes totally symmetric between negative and positive.
Yeah, so you could, we've been struggling with the value 0, whether to include it or not.
Well, I would include it half.
Okay.
Then it becomes fully
Okay,
symmetric
okay.
between the negative cases and
that's
the
a good
positive
idea.
cases.
Yeah.
And I wonder whether some of your limits, which are now 1, would then turn into 1/2, which is interesting.
Okay, good point. Interesting. We haven't thought about that to sort of really make the situation symmetric by including the value 0 with only half. No, Remco was saying you do not look at mu of the closed interval 0. You take the open interval, but you add 1/2 of the value, the atom at 0. Sometimes
because in some of your limits, you actually get the limit 1, and it's unclear whether the limit 1 actually arises from everybody having bias 0, or from sort of everybody having a positive bias. And here you break that symmetry.
We might, that would be an interesting thing to look at.
Yeah, so I was wondering if you thought about how degree-degree correlations play a role, because in the models that you analyze, right, locally tree-like, so at least the models that I see, they have basically they're independent, and then indeed what you observe is that if your degree distribution has a very thick tail, then your significance is in general much higher, right? So these values are much higher. While if your degree distribution is much more sort of homogeneous, then actually the significance is much lower. So I'm wondering, what if I take another random graph model that has a local limit, but that has, say, for example, positive correlations?
Yeah, that would be interesting to look at. In the model that I skipped, which was an inhomogeneous version of the Ederson graph, you see that the inhomogeneity plays a role. It plays out significantly in the French. It's a different thing from what you are suggesting, but models with dependencies it would be interesting to see how that reflects. So your computations are going to be harder, but maybe just by proving inequalities, we could do something. That's also an interesting suggestion.
Question, I'm not sure in a directed setting, is it always true that you have, under which condition you have a friendship paradox?
No, because when we proved that it's always non-negative, we use the symmetrization.
Yeah, this I know. In fact, in an undirected, you only need some variability in the degree structure. In a direct...
Degrees, right?
Yeah, the question is in and out the degree paradox. But it's unclear whether, I don't know, I knew it for the undirected, I don't know for the directed if it's known which minimal condition guarantees the positive, not the quantifiable strength. But
if I want to confuse students, I ask the questions about the friendship paradox and directed graph.
And?
Is it like what your follows have what follows that you do? Or like this, like graph conversions and both of them are correct?
I think we would need to ask Federico to dive into this.
Is it clear from the
question
algebra on a finite graph?
Okay. Yeah.
So, thanks, Frank, again.
Thank you so much.